Here we are given a half-wave rectified sine wave, f of t, so this is what the sine wave would have looked like before rectification. And after rectification, the negative half cycles have become 0. And the question is asking to find the period, the fundamental frequency, and the DC value A0. And it's asking to comment on whether the signal is even, odd, or neither. So for 5 marks, you have 1, 2, 3, 4 things to mention. So first of all, the period, so this is clearly a periodic signal. The period is going to be the time it takes to repeat the signal. So it's this time here, and it's probably easier to measure that from here to here. So the period is clearly 4 pi. So that's the first thing to mention, that t equals 4 pi. So the period repeats every 4 pi. It also wants omega naught. So omega naught, the fundamental frequency, is the reciprocal of the period. It's actually 2 pi divided by the period. So that's 2 pi over 4 pi. So we can write omega naught equals half, and the unit is radians per second. So the units for the period are time, the units for the fundamental frequency are radians per second. If you wanted to find the fundamental frequency in hertz, it would be 1 over t. So 1 over 4 pi, and that would be in hertz. But that's not being asked for here. The next part, or the next thing we need to find, is the DC value. So to find the DC value, you'd need to find the area. So A0, by definition, is the integral from 0 to t f of t dt. So we've found t, so that's good. We haven't yet found f of t. So f of t looks like it's a sine wave, but it's only a sine wave from 0 to 2 pi. It's not a sine wave from 2 pi to 4 pi. So let's write out what we've discovered. 1 over t, that means 1 over 4 pi. And you'll integrate, instead of integrating to 4 pi, we'll only integrate to 2 pi, because beyond 2 pi is just 0. Now f of t is a sine wave with a period of 4 pi. So that would be sine t over 2 dt. So that's the expression we'd need to find the DC value. This is an easy enough expression to integrate. So that will give me, first of all, this sine wave doesn't have an amplitude of 1, it has an amplitude of A, so really there should have been an A there. So if I take the constants outside of the question goes on to ask for the Fourier coefficients, the cosine and sine coefficients, an and bn, for this half-wave rectified signal. So to do that, first of all, we're going to need an expression for the non-zero part of this wave, and it looks like it's a sinusoidal wave, so it's a sine wave, or at least it's part of a sine wave. But it looks like it's a sine wave with a period of 4 pi rather than 2 pi. So it covers half a cycle in 2 pi. So the sine wave itself would have looked something like that. So that would be a sine wave that's compressed by a factor of 2 or stretched by a factor of half. So that's sine t over 2. So that's what you would need to have a sine wave like that. And to have an amplitude of a, you would need that to be a times sine t over 2. Now to find the cosine coefficients, you would need an integration. You would need to integrate f of t times cosine n omega naught t. You'd integrate that across one complete period from 0 to t, and then you would multiply by 2 over t. So if I replace f of t with a sine t over 2, that gives me that. Now we have a sine multiplied by a cosine. That's not easy to integrate, but we have a number of identities that we can use. So when you have a sine multiplied by a cosine, you can replace that with half sine of the sum plus sine of the difference. And that's easy to integrate, and that's easy to integrate. So the sum, if you add t over 2 plus n t over 2, you get t over 2 plus n t over 2. And then the difference, t over 2 minus n t over 2, will be that. And between them, we have a plus. And the half, I've simply divided that by 2. So before we integrate each of these, we can add these together because you have your independent variable t as a common factor. So you can take t as a common factor in each of those. And there we have t here and t there. So now to integrate this, we would simply replace these with minus cosine and then divide by this coefficient here. So sine would become minus cosine, and this sine would also become minus cosine, and then you just divide by the coefficient there. Now obviously this is only possible if you're allowed to divide by that. If n happens to be 1, you can't do that. So this only works when n isn't equal to 1. So we need to separately find what this would be if n equals 1, possibly by going back to the original integral and not using this identity. Okay, so next step, we can turn this or these divisions into multiplications. So I turned the fraction upside down and turned it into multiplication. Now all you need to do is replace the limits, the 2 pi, and replace the zeros. So the 2 cancels with the 2 in the denominator, and you simply have cosine n plus 1 pi and cosine 1 minus n pi. And if you think about it, cosine any multiple of pi is going to be either plus 1 or minus 1, depending on whether n is even or odd. So if you think about it, whenever n is odd, say n equals 3, then 3 plus 1 is 4, and cosine 4 pi is going to be 1. Whereas if n was even, 2 plus 1 is 3, and cosine 3 pi is minus 1. So if n is odd, you end up with that, which simplifies to 0, and if n is even, you end up with that, which simplifies. But I'm going to leave that there for a second, and I'm going to go back to the fact that we said n isn't equal to 1, but what if n is equal to 1? If n was equal to 1, then we would need to find a1 separately. So if we replace 1 for n there, we end up with sine, cosine. And because these are the same, we can then use a separate identity, the double angle identity, where sine, cosine is simply half sine twice the angle. And that's easier to deal with because we don't have to divide by 1 minus n. So sine t over 2 twice the angle, that will give us sine t, and the integral of sine is simply minus cosine. So that's looking much easier. And then, you replace your limits, and cosine 2 pi and cosine 0 are both the same, so you end up with 0. So a1 equals 0, basically. That's what we've just found. So now if we go back to our original expression for an, remember up here, our expression for an that we were working on, this cancels with this, and this cancels with that. So you end up with 0 for odd values of n, including 1, and this for even values, because this and this add up together, and this and that add up together. So these 2's we can probably cancel with that 2. Yep, so you end up, if you unify the denominators, the n's cancel out, and you end up with 2 in the numerator, and that, let me rewrite that. So 1 minus n minus 1 and plus 1 will give you n squared minus 1. That just looks a little bit neater. So that's my final expression for an. I think we can leave it at that. But this is only for even values of n. And for odd values of n, it's 0. It would be nice if we could combine these two into a single expression. So there are various ways in which you can codify the fact that this is non-zero for even values. So if I multiply by this factor here, whenever this n is odd, you'll get a 1 here, and 1 minus 1 is 0. So that'll ensure you get a 0. And whenever n is even, like 2 plus 1 is 3, minus 1 to the power 3 will be minus 1. So 1 minus minus 1 is 2. So you end up with a 2, and that's what we want there. So you can use this. Some people use some kind of multiple of sine pi over 2 or cosine pi. You can do anything that's equivalent to that in order to combine these into a single expression. Do you have to do that? Can you leave it like that? You can probably leave it like that. But as you'll see in the next part of the question, it does want you to write it out as a summation, and it's awkward to put something like that in a summation. You need somehow to codify the fact that you have zeros for the odds. Okay, so that was for the an. How do we find these sine coefficients, the bn? It's exactly the same integration. You simply multiply f of t times the sine. So this time you're going to have sine multiplied by sine. So you're going to use the other identity where you have cosine of the difference minus cosine of the sum. So otherwise, it's very similar to what we were doing earlier. So cosine of the difference and cosine of the sum. And between them you have a minus sign. So again, we're going to take t as a common factor here. That's your t. And then we're going to integrate cosine to give me sine. And then we divide by the coefficient. And then we say, wait, n cannot be equal to 1. So this is true when n isn't equal to 1 because we can't divide by 1 minus 1. So if we carry on, we turn the division into multiplication. We turn the division into multiplication. Now we just substitute the limits. And again, sine 2 pi and sine 0 are both 0. So you end up with a lot of zeros because any multiple of pi for a sine, you're going to get 0. So we've just shown that the b terms are all 0, except when n equals 1. So when n equals 1, slightly different. It's just we don't have an n there, we have 1. So now we can use the double angle formula. When you have sine x squared, that will give you 1 minus cosine twice the angle. So you can replace sine times sine with 1 minus cosine. And the integration of cosine is simply sine. The integration of 1 will actually give you t. So you end up with t minus cosine 2t. Now, sine 2 pi and sine 0 are both 0, but this is the one that matters when you have 2 pi replaced in there. So that will simplify to a over 2. So the sine is just 0. We end up with b1 equals a over 2, and that's an important finding. So all the b's are 0 except b1. So now we've found b1, we've found bn, we've found an, and we found a0, sorry, a1. I think we found a0 in the previous part. So now we should be ready to write our expression, and that's the next part of this question. It says express f of t as a Fourier series. So write out a0, an, and bn. So we've already found these terms. All we need to do is write it neatly in the form of a Fourier series for an extra 5 marks. So that's literally a one-line answer. A0, we found that earlier. An, that's this term here. And bn is 0 except when we're talking about b1, in which case the answer is a over 2. So that's all you'd need to write for the 5 marks. So this needs to match what you had in part A, and these need to match what you found above. The final part of the question asks for the autocorrelation of f of t. Now, to find the autocorrelation, what you want is the autocorrelation integration. So it's f of t multiplied by f of t plus the shift tau. So this shift tau is the same as that shift. And this t is your variable there. So if you think of it, if I were to sketch the axes like that, and if you think of it like this, this is f of t, then f of t plus tau, this is a version of f of t that's shifted to the left by tau. So it'll look something like this. Okay, so if I were to move this across from minus infinity all the way to infinity, what we're integrating is really the parts where they are non-zero and they overlap. So there's no point integrating before 0, and there's no point integrating. So if this is 2 pi and this is minus tau, this will be 2 pi minus tau. So if we're going to integrate, even though we're supposed to integrate from minus infinity to infinity, it's enough to integrate over that period there, from 0 to 2 pi minus tau. So I'll just replace my f of t with what I know f of t looks like, and I'll do it again, but this time I'll add the shift to my independent variable t, and I'll change the limits. Instead of minus infinity to infinity, I'm integrating to from 0 to 2 pi minus tau. So again, we're going to use the identity. When you have a product of two sines, then it's half the difference of two cosines, where one is the difference of the two and one is the sum of the two arguments. So the difference, t over 2 minus t plus tau over 2, is simply that, and the sum is that. Now, integrating a cosine is simply a sine, and this will be sine, and then you divide by the coefficient of t. In this case, you don't have a t, so this actually isn't a cosine. This is just a constant, because there is no independent variable here. There is no t. So this is, you treat this as a constant, but you treat this as a cosine. So the integral of cosine is sine. The integral of this is simply whatever it is multiplied by t. And the derivative of this with respect to t is simply 1, so you'd simply divide by 1. So we're almost there. We've multiplied by t, and we've got the cosine to give me a sine. These are my limits. I now simply need to replace this once, twice, and then this once, twice, and we're done. So replacing replacing 2 pi minus tau here gives me that. So if you like, that is that, and that, and then replacing 0, that's my 0, and that's the result of basically adding 0 to tau. Now we simply need to tidy this expression up, so that 0 cancels. Sine, when you add 2 pi, it has no effect. That minus, because sine is odd, sine minus tau over 2 just means minus sine tau over 2. So that will simplify with that. So that minus becomes a plus, and we can remove that minus, remove the 2 pi. So this now becomes the same as that. That I've removed. So we now have these two combining into that and that there. And that is your autocorrelation function. That's only for tau between 0 and 2 pi. Clearly, between 2 pi and 4 pi, the autocorrelation will be 0, and then it will be periodic. It will continue to repeat with a period of 2 pi. Sorry, a period of 4 pi. So this is it's a raised cosine, or it's a cosine that's multiplied by a line, so it will probably look like something like that. The question doesn't ask for a sketch, so you don't need to do anything more. You simply need to specify that this is only true between the limits that we actually integrated, which is here to here. So it's true from 0 to 2 pi, but it's not true beyond 2 pi, i.e. from 2 pi to 4 pi, the autocorrelation is 0. So that's the end for this question. This is what you would need to do for the 5 marks for that question.